Hi everyone, I'm Liron Faybish, and again, first I want to thank you all for joining my talk. Today we are going to talk about keeping sensitive data safe using recommendation systems. So let's talk a bit about recommendation systems. This is me, and usually in Netflix I like watching romantic comedies such as those movies. So it will be nice from Netflix to recommend me more of those movies that I'll probably like to watch, like this one. That's the basic of recommendation systems, suggesting few items that you'll probably like based on your previous preferences. It could be in a various of fields like videos, foods, clothes, and so on. Now if we are back to our Netflix example, what if someday I watched some documentary about the French Revolution? This movie is not connected to my previous movies and is not aligned with my previous preferences. Of course, it could be someone else who is using my accounts, or it's just me who wants to try new things and watch something different. But in both cases, this scenario doesn't represent my regular behavior, and there is something weird that's going on. But we are not here to get new movies recommendations. You can do that later. We are here to talk about information security and about protecting the data in our organizations. Although these two subjects, recommendation systems and anomaly detection, don't seem to be related to each other, in this talk I'll show you how you can twist recommendation system methods and use it in an opposite direction in order to protect your organization and keep your data safe and secure. You will see that sometimes you need to go the opposite way in order to get to the right direction. Now a few words about myself. I'm a data scientist on PayPal for the past 6 years. I am part of the cybersecurity threat oversight team, which is part of the information security organization. We are a team of security researchers where each one has a different perspective and unique point of view in order to cover as many security issues as possible. My role is finding machine learning solutions for information security problems. And in addition, I have MSc in information systems and software engineering from Ben-Gurion University. So our objective for today is to learn and understand how we can protect our organization and the sensitive data in it. Many organizations are using a massive amount of data for their day-to-day job. And usually most of the organizations are using databases to store the data, and users are performing queries in order to access, extract, or update the data. Sometimes this data might be sensitive and shouldn't be exposed to all users. For example, data like passwords, phone numbers, addresses, and accounts is very sensitive and shouldn't be exfiltrated out of the organization. Keeping this data safe and secure is one of the main issues that most of the organization needs to deal with, because it can cause real damage to the company if this data is leaking out to the wrong hands. So the problem we are trying to solve is the need to improve the control we have in the organization on our sensitive data. It means that we need to find a way for keeping this data safe and prevent potential security incidents and any possible misusage of this data. It means that we need to make sure that only authorized users will access it and detect any different behaviors in the user's data access patterns. In this talk, I'll show you how you can use recommendation system methods for the problem of anomaly detection and how it can help us detecting unauthorized access to our databases. At the beginning, we will talk about recommendation systems in general, and specifically about implicit feedback and its implementation in Python. Afterward, we will talk about the domain of databases access and how we can use recommendation systems for detecting anomalies in that domain, and I'll show you the experiments I made and how it's proving the accuracy of the method. So let's start with recommendation systems. As I mentioned earlier, in recommendation systems, usually we have several items, and the goal is to predict a rating a user would give to each item and suggest relevant items for him. The most popular method for finding those recommendations is called collaborative filtering, which based on the assumption that people who agreed in the past will tend to agree in the future. Collaborative filtering is using similarity scores between users and items in order to provide recommendations. For example, if we have two users who usually eats a burger and a salad every day, and one user is buying a cake for dessert one day, so it will be probably a good option to suggest the other user to buy a cake for dessert as well. There are two types of feedback when talking about recommendation systems. One is explicit feedback, where we have a direct input from the users regarding their preferences. This way we know exactly how much a user like or dislike a particular item by providing a numerical rating to it. For example, a user is rating a movie from 1 to 5 stars, or rating a dish in a restaurant from 1 to 10 according to how much he likes it. But users probably don't want to spend time rating the items they are using, so usually this type of feedback is hard to get. Another type of feedback which is more popular is implicit feedback, where all we have is only the users and the items interaction. It is data we gather from the user's behavior with no ratings or specific actions needed from the user. For example, if a user has watched a movie for 5 times, the system infers that the user is interested in it. More example of implicit feedback could be items the user purchased, how many times they played a song or watched a movie, how much time they spend reading a specific article, and so on. The upside of implicit feedback is that we have a lot more data. But the downside is that it's way more noisy and we can't always understand its meaning. For example, with stars rating, we know that 1 star means that the user didn't like that item, and 5 stars means that they really loved it. But when watching a movie, it could be that the user watched it and hated it, or loved it, or somewhere in between. And if he didn't watch the movie at all, it might be since he doesn't like it, or that he would love it if he just knew about it. Later in this talk, I'll explain how we can overcome this problem. Here in our domain, the type of the data we are dealing with is implicit data. There are a lot of methods for calculating those ratings. One of them is called matrix factorization. In this method, the past ratings are stored in a sparse user item matrix, where each cell stands for the rating a user is giving to an item. And the matrix is sparse because each user has only few related items, and usually there are no users who rated all items. The matrix factorization method suggests using low-dimensional representation of users and items in a shared latent factor space. And by using those user item latent space, we can infer unobserved preferences. The idea is basically to take the large user item matrix and factor it into some smaller representation of the original data. And the multiplication of the user and the item matrices gives us the predicted rating matrix. For example, in order to calculate the predicted rating a user U would give to an item I, we need to calculate the multiplication of row U in the user's matrix with column I in the items matrix, which is the UI cell in the predicted rating matrix. So the goal is that the predicted rating matrix will reflect the true preferences of the users. Common loss function for user U and item I can be expressed as the following, where we are trying to minimize the squared error of the difference between the real rating and the predicted rating, which is the dot product of the user and the item vectors, and in addition there is also the regularization term in order to prevent overfitting. Minimizing this formula using the regular optimization methods works better for explicit feedback, but doesn't work well when dealing with implicit feedback data. The main difference between implicit and explicit feedback is how we are dealing with missing values. In explicit data, it's just unknown data. But with implicit feedback, we cannot assume that, since there are some information in these unknown values. So we need to find a way to learn from the missing data. The approach we are going to use here with our implicit dataset is based on the method mentioned in the paper, collaborative filtering for implicit feedback datasets. In the method mentioned in the paper, they used binary preference. Has the user observed the item or not? And they merged that preference with the weight of confidence we have for that score, which is the strength of the preference. Missing values are negative preference with low confidence, and existing values are positive preference but with a high confidence value. In the paper, they used RUI for representing the observation for user actions. For example, in the domain of watching movies, RUI could be the amount of times user U watched movie I. The next formula is PUI, which is the preference of user U to item I, and is equal to 1 if RUI is greater than 0, which means that the user consumed the item I, or it will be equal to 0 if the user didn't interact with the item at all. Later we are calculating the confidence. CUI is equal to 1 plus alpha multiplied by RUI. The confidence is higher when the user interacts more with the item and uses it more often. And the rate that the confidence increases is set using a linear scaling factor alpha, and I also added 1 in order to have a minimal confidence even if R is equal to 0. Now we are trying to minimize the following cost function, which is the confidence multiplied by the square difference between the preference and the dot product of the user and the item vectors, and again adding the regularization term. This cost function depends on m and n, where m is the number of users and n is the number of items. And even for typical datasets, m multiplies n can easily reach a few billion. And the regular optimization methods such as stochastic gradient descent, SGD, wouldn't work well for this type of data. Therefore, in the paper, they offer to use an alternative optimization method, which is the alternate least squares algorithm, ALS. This method suggests fixing each factor at a time. And if we are fixing the user factors or the item factors, we can calculate the global minimum. It means that we are alternating between recomputing the user factors and the item factors. And when fixing either the user or the item factors, the cost function became quadratic, so its global minimum can be easily computed, and each step is guaranteed to lower the value of the cost function. The full mathematical calculation of this method is out of the scope of that presentation, and you can read about it later. So now, after solving everything and calculated the matrices, we can finally move to the recommendation process. In Python, there is an implementation of this algorithm in the implicit library. This library provides fast Python implementation of several different popular recommendation algorithms for implicit feedback datasets, and one of them is the alternating least squares algorithm as described in the paper. In order to install it, you just need to do pip install implicit, and you'll be able to import it and use it. For using the ALS algorithm, you need to initialize the model first using implicit.als.alternating least squares, and then choose the number of factors, which is the number of latent features to compute, then choose the regularization factor to use, and also choose the number of ALS iterations to use when fitting the data. Later, we need to create the confidence matrix. So we are choosing the alpha value, which here it's 40, and multiply it by the sparse user item matrix. Then we are fitting the data to the model using this confidence matrix and creating our model. And now that we have the trained model, we can move to the recommendation. We can recommend items for the user using the recommend function. We are choosing the user we want to recommend items to, and we are also choosing the number of items to recommend. And the function also needs the original user item matrix in order to filter out the already used items. The function calculates the top n best recommended items for the users and returns a list of items IDs and a corresponding score for each item. For example, item number 566 received a score of 0.86, which is higher than the item 166 received, which is 0.7. One more interesting function is the rank items function, where you can choose a user and a set of items you want to rank, and the model will calculate their score and rank the items according to the preference of the user. Again, the function returns the IDs of the items along with their score. As you can see, the scores aren't always between 0 and 1. It happens because there is no explicit scale here. The scores are used only for ranking and sorting the recommendations, where the higher score means the most recommended item. When calculating the dot product of the users and the item vectors, we are trying to make it as close as possible to the real preferences. But since there are no boundaries, it can take any possible value. By finding the optimal parameters, we are pushing those values close to 0 and 1. But when adding the regularization term and the confidence weight, those additional factors may push them in different directions. So we don't always end up with 0 to 1 values. So now that we know how recommendation system works and how to use it properly, we can move to the real problem we are here to talk about, which is keeping our data safe and analyzing our database's access patterns. Our domain is database's access, and the actions we observe are users who access to tables and extract or update the data in it. So our objects are users and tables, and the relationship is that the users are consuming the tables, so the tables are the items. Users are accessing to tables using queries, so we are looking on the amount of queries each user performed on each table, and that would be our implicit feedback. In general, high amount of queries on a table means that the user liked the table, it's relevant for him. But if there is a low amount of queries on a table, it means that the user disliked the table, or as we discussed a few minutes ago, it may be because he needed it only for a few times. In addition, if the user didn't access a table at all, it could be because this table is irrelevant to him, or because he didn't know about it or didn't have the chance to use it yet. And again, that's exactly why in the algorithm we are using, they added the confidence value on the user preference. And in the cases where we don't have many interactions with the table, the confidence will be low. So the problem we are trying to solve here is finding the anomalies in those actions of accesses to tables. Basically, it is events of unexpected or unauthorized access to tables. For example, if someone is working on a project of type X, he is usually accessing tables that related to this project X because that's what he needs to perform his job. But what if suddenly he's accessing odd tables, which doesn't relate to his project and doesn't relate to any one of his team members' project, and might contain sensitive data that he doesn't supposed to have access to at all? For example, we don't want someone from the user interface team in Netflix will access the customer's data. This data isn't relevant for user interface, and there is no excuse for this user to access this data. So we need to prevent those events and keep our data safe. We should create an alert for those kind of actions, so we'll be able to protect this data and make sure it doesn't exfiltrate it out of the organization. But our recommendation system is related to all of it, and how it can help us solve our problem. As we mentioned above, our goal is detecting anomalies in the user's usage patterns. Detect when the user is behaving differently from the way he's supposed to behave, and performing actions that doesn't fit with his previous actions. Usually in recommendation systems, we are looking for items that the user is supposed to like and recommend it to him. But here in this case, we are looking for the outliers, which is the opposite direction of recommendations, the items that the user is unlikely to use. And that's what I want you to take from that presentation, that sometimes you need to switch your algorithm and use it in an opposite way in order to solve your problem. For example, in the movies domain, instead of focusing on movies the user would like, we are looking for the least expected movies, with the lowest probability that this user would watch. Think about me with the French documentary movie we talked about. I want to know when there is a change in the user's behavior. So in our solution, we are looking for those unrecommended items that the user is not supposed to use, and alert when he's using those items and might cause dangerous consequences to the organization. So we need to build a recommendation model based on the database's access logs. We need to count the amount of queries each user performed on each table, and this will be our implicit data, which is the sparse user item metrics. We are building the ALS implicit model using the Python library. We are setting the values for the regularization term, the regularization factor, the number of ALS iterations, the number of latent factor to use, and the value of alpha, the value of the scaling factor alpha. We decided to train the model using 6 months of queries data, so we'll have enough data for training the model. We also decided to count new access to a table only if the user is accessing the table using different queries on the same day. It means that if the user is using the same query for several times in the same day, we will count it only once. But in the next day, it will be counted again as a new query. We did that because we wanted to remove automated queries that runs the same query over and over again, and create a really high amount of accesses to tables. It creates a lot of noise in the data, and we wanted to reduce that noise and make the model as close as possible to the real access patterns. In addition, we also set a threshold for minimum access for users and tables, and we filtered out rare users who accessed only few tables, and also all is good? לא? Okay, so we filtered out rare users who accessed only few tables, and also tables that almost no users have access to. So now we have a trained model that can calculate recommendations. But how can we know that it is actually working? In order to prove the accuracy of the model, we performed 2 experiments where we tested the output of the model. In the first experiment, we simulated multiple accesses to tables and checked the score the model gave to each item, to each access. We created a test set of 500 events of users who access to tables, and we decided to consider for the test set only events of users who access to a table for more than 10 times, so we'll be able to be sure that this table is indeed relevant for the user. We chose those events because we are dealing with implicit data. And if we are choosing a user who accesses to a table only once, it could be because he accessed it by mistake and it's irrelevant to him. And we wanted to be sure that we are testing only known preferences. So we trained the model using the access data, and then we calculated the scores for the test set and plotted the results on the following histogram. As can be seen in the histogram, almost all of the observation received high score, around 1, which indicates the accuracy of the model, since it means that the model is predicting the scores correctly according to the real preference of the user, because we chose for the test set only items that we know for sure that the user actually liked, because he used it for more than 10 times. The second experiment we made is based on the assumption that in the world of databases access, similar users who works on the same team or works on the same types of project will access the same groups of tables that related to their project or to their team. And the outliers are when someone is accessing a table that he didn't access before, and it doesn't relate to any other of his previous tables or to any of the tables of his similar user group. So in order to simulate good and bad access to tables, we are choosing 500 random users, and for each user we are choosing 2 unseen tables that this user never accessed before. The first table is taken from the group of tables that his team already accessed and used, and the second table is taken from the group of tables that no one from his team accessed before. Now we are feeding those scenarios into the model and we are calculating the scores. In order to evaluate the results, we calculated the kernel density estimation of the scores. And as can be seen in the graph, the blue tables, which are the tables taken from the same team, received higher scores than the red tables that was taken from other users. You can see the separation between the blue and the red tables, and how the outliers we simulated received a lower score than the blue relevant tables. In addition, you can see that most of the scores in the red group are around 0, and most of the scores in the blue group are around 1. It means that the model indeed was able to identify the suspicious access to the unexpected tables and separate those scores from the good data. In addition, we also calculated the ROC curve and the AUC, and it was around 90, which is another indicator that our ALS model is working the way we wanted it to work. So now we have a system that gets us input and access to a table, process it through the model, and generate a score for each access. And this score indicates how normal or abnormal this access is. And in order to find the anomalies, we need to set a threshold based on the scores the model calculated. And if there is a new access to a table that received a score above this threshold, it's a normal event. And if it receives a score below this threshold, it's an anomaly. I also wanted to share that after creating this project, testing the model, and evaluating it, me and my colleagues in PayPal decided to file this idea as a patent in the US Patent Office, and now you can find it and read all about it in Google Patents. Possible future steps on this area could be using this mechanism for the granting access process in the organization. For example, if a user is requesting an access to a specific table, we can calculate the score for that access, and if this score is low, which means that the probability that this table is relevant for that user is low, maybe we should ask his manager before granting that access to him. One more thing could be learning and getting insights from the scores and leverage team collaborations. For example, creating a team's clusters according to their preference vectors, and suggest those teams, which is in the same cluster, to collaborate and learn from each other since they are working on the same type of data. Obviously, there are some challenges in this method. For example, possible challenge could be that we have different level of sensitivity for each table, and that each table should be handled in a different way. We can identify the set of sensitive data and give it smaller threshold, so we'll be able to control the sensitivity of that access. And tables that contains more sensitive data will get more focus, while tables with regular data will get higher threshold. This way, we can play with the threshold in order to control the noisiness of the alerts according to the sensitivity of the data. Another challenge could be changes inside the organization, employees who are moving from one team to another, changes of responsibilities, and so on. This could confuse the model because now we have users who access to tables that are far from their previous tables. We can solve this problem by defining some grace time when we are learning the new vectors again, and canceling the alerts from the team for a while until we are learning the new updated vectors. For conclusion, if there is one thing I want you to take from that presentation, is that sometimes you need to go the opposite way in order to solve your problem and to get to the right direction. I presented the idea of using recommendation systems for the problem of anomaly detection. We talked about recommendation systems in general and specifically about implicit feedback and the ALS algorithm. Later, we discussed about how can we use this algorithm for the database's access problem, and about using the opposite direction, the direction of the recommendation process, in order to find anomalies instead of recommendations. Now we can detect unauthorized access to our tables, get a score for each new access, and alert or block that event accordingly. And once you'll embrace this way of thinking and implement into your algorithm the main aspects I just covered, we will all get safer organizations and better protections on our data. Thank you for listening to my talk. If you have any questions, let me know.